We are going to look at solutions to an old calculus final exam that I've given to my class. And so the first question in front of you deals with limits, and it's asking you to evaluate the following limits. So when you're looking at limits, the first thing that you want to do is do direct substitution. If we do direct substitution and we get an indeterminate form of 0 over 0 or infinity over infinity, then we need to manipulate our limit before we go through and take it again. And so for this first problem, we're looking at the limit as x is approaching -1 of 3x cubed minus 3x squared minus 6x. That whole quantity is in the numerator and it's divided by the quantity x squared plus x. And so if we did direct substitution, plugging in -1 wherever we see an x, we have 3 times -1 cubed minus 3 times -1 squared minus 6 times -1, all divided by -1 squared plus -1. So doing order of operations to simplify this expression, we have -1 cubed, which is -1, times our 3 out front is -3. -1 squared is 1, times the -3 out front is -3 or minus 3. And then -6 times -1 is plus 6. All divided by -1 quantity squared, which is +1, plus a -1, so like -1. And I notice I would get 0 over 0. So right now I can see that we have an indeterminate form. And so there's two ways to proceed. We've now learned L'Hopital's rule, so we can go through and use L'Hopital's rule on this, or we can factor and simplify by canceling out like factors in our numerator and denominator. So let's go through and let's just see if we can factor this nicely. If I factor my numerator, I notice I can factor out a 3x from all three of those terms. Pulling out a 3x, I get x squared minus x minus a 2 all over, and I notice I can factor out an x in my denominator. Factoring out an x, I would get x plus 1. So I notice I can reduce a little bit. I have a common factor of x in my numerator and denominator. I can go through and I could try to do direct substitution again. Or I notice that I can factor this a little further and that we may have common factors in our numerator denominator, which would give me an indeterminate form if I just went through and did direct substitution again. So let's go ahead and factor this first. Factoring x squared minus x minus 2, I'm looking for two numbers that multiply to give me -2 and add to give me -1. Those two numbers are -2 and +1. So I would factor that expression as x minus 2 times x plus 1. This is all divided by x plus 1. So notice we have common factors now again in our numerator denominator, and this time it's x plus 1. And so we are left with a limit as x is approaching -1 of x minus 2. So now when we go through and we do our direct substitution here and we plug in -1 wherever we see an x, we get back -1 minus 2, which gives us -3. Okay, so I just want you to be aware that where I put in my showing my work, where I put the limit and where I did not put the limit. So whenever I was substituting my value of x, what we were approaching, into the function, I did not write the limit. If I was simplifying, I needed to carry that limit down until I went in and I placed in the value of what x was approaching. So you need to start making sure that you're writing your stuff mathematically correctly as you're showing your work. And so if you don't bring down that limit, when I'm grading it, I may dock off some points if you're in my class taking the test. Okay, so let's now look at part B. So part B says we're looking at the limit as x is approaching 9 of, let's square root of x minus 3, which is in my numerator, all over 9 minus x. So again, I would start by direct substitution. Just because I know myself, I'm guessing that I'm going to get an indeterminate form again. And if I do my direct substitution and plug in 9 wherever I see an x, I notice that I get square root of 9 minus 3, which is 3 minus 3 is 0, all over 9 minus 9, which is 0. So I'm again getting that indeterminate form. That indeterminate form, again, we're not going to stop. We're not done. If I had gotten 0 over a number, I would have been okay. I could have said that's 0. Or if I had gotten a number other than 0 over 0, I could have stopped and said that's undefined. But 0 over 0 is an indeterminate form, so I need to go back and I need to work through this. I could use L'Hopital's rule and see if that would work. Or I know that if I have radicals and a rational expression of what I'm trying to take the limit of, and I get that indeterminate form, then a good rule is to multiply by the conjugate. So in this case, we're going to multiply what I call a fancy one to both my numerator and denominator. We're going to multiply the conjugate of that expression of the two terms with a radical. So the conjugate of square root of x minus 3, all we're doing is we're changing the sign in between. So we're getting square root of x plus 3. I want to multiply by 1, so all over square root of x plus 3. So multiplying 3 by a conjugate of the radical of two terms, it's giving us a difference of 2 squares. And so when we distribute that out, that is going to get rid of that radical in our numerator here. And so I'm looking at the limit as x is approaching 9. So square root of x minus 3 times square root of x plus 3 gives me the square root of x quantity squared, which is x, minus 3 quantity squared, which is 9. All over, I notice that I have a 9 minus x in my denominator. I want it to look like x minus 9. So if I factor out a -1 from the 9 minus x, that's the same thing as x minus 9, or -9 plus x. I'm just changing the order of that subtraction piece. All times. So in the denominator, I still have that square root of x plus 3. You do not want to distribute that piece where it's not the conjugate of it, because doing that, then we don't see that we have common factors that we can cancel. So we can cancel the common factors of x minus 9 in here. And now we're left with a limit as x is approaching 9. Our numerator, we're left with 1. Maybe we can pull that negative out front from the denominator, all over the square root of x plus 3. So now when we plug in our values for x, we don't get that indeterminate form. So we have -1 all over the square root of 9 plus 3, which is equal to -1 all over square root of 9 is 3, and 3 plus 3 gives us 6. So we get -1/6 back. So problem or part C of this problem, we have the limit as x is approaching 3 of 1 over x minus 1 over 3. That quantity is in the numerator, all over x minus 3. Again, I would do direct substitution. I notice again that if I go and do my direct substitution and plug in 3 wherever I see an x, I would get 1/3 minus 1/3 in the numerator, which is 0, all over 3 minus 3 in the denominator, which is also 0. So again, I have an indeterminate form, so I need to go back and I need to manipulate this. So if you have a complex fraction, one way to deal with this is to clear our complex fraction. I tend to like to clear my complex fractions by looking at my fractions within my fraction, my main fraction, by my LCD. So I'm looking for my least common denominator of x and 3, which is 3x. And let's use that common denominator to multiply what we're taking the limit of by that fancy one. So in our case, 3x over 3x. So when I distribute my 3x to the fractions in my numerator, notice that my denominator is going to cancel. So I have this 3x all times 1 over x. The x's cancel, and I'm left with just a 3. Minus distributing 3x to my 1/3. Well, the 3's cancel, and I'm left with just an x. All over, I'm not going to distribute in my denominator. I'm going to keep it in factored form as x minus 3 all times 3x. So again, I noticed that I almost have the same factor in the numerator and denominator. I'm just off by a -1. And so we want to go through and we want to factor out the -1 from either the numerator or denominator. So if I pull it out of my numerator, I would be left with -3 plus x, which I could write as x minus 3, all over x minus 3, all times 3x. Canceling like terms in the numerator denominator, we can now cancel the factor that we have in common, x minus 3. And so we're left with a limit as x is approaching 3 of -1 all over 3x. And so doing direct substitution, plugging in 3 wherever we see an x, we're going to get back -1 all over 3 times 3, which gives us back -1/9. Okay, so those were some tricks or things that we could deal with by dealing with limits that gave us an indeterminate form. If you like, and if it works, each one of those were in the form, that indeterminate form, where we could have tried L'Hopital's rule. Because I didn't tell you which method to use, you can use the method of your choice. Okay, so now moving down to part D of our problem. The problem states that the limit is x is approaching infinity of our numerator, which is the quantity x raised to the 15th power plus 8x raised to the 12th power plus 1, all divided by 1 minus 2x to the 15th power. I notice if I go in here and I plug in infinity wherever I see an x, I get infinity to the 15th power, which is infinity, plus 8 times infinity to the 12th power is still infinity, plus 1 still gives me infinity. So here I get infinity divided by, and so now if I go in and plug in infinity wherever I see an x in the denominator, I get 1 minus 2 times infinity raised to the 15th. Well, infinity to the 15th is infinity times that -2 in front is negative infinity plus 1 is negative infinity. I technically can bring that negative out front, and so I get infinity all over infinity, which is an indeterminate form, which means that I need to go back and I need to simplify. So I noticed in this case, if we use L'Hopital's rule, it's going to take me a while. I would have to actually go through here and use L'Hopital's rule 15 times because I would still keep getting infinity over infinity. Or we can use the trick. If we get infinity over infinity, look at the degree of the denominator, which is 15. And so we're going to multiply this by the fancy one of your variable raised to that highest power in the denominator divided by, so 1 over x to the 15th time all over 1 over x to the 15th. So multiplying what we're taking the limit of by that fancy one, when we go back in here and we substitute or we distribute, we get x to the 15th over x to the 15th, which gives me back 1, plus 8x to the 12th over x to the 15th. Using rules of exponents, I'm left with 8 in the numerator all over x to the 3rd power, plus 1 times 1 over x to the 15th is 1 over x to the 15th. Divided by, so distributing this in our denominator, 1 times 1 over x to the 15th is 1 over x to the 15th, minus 2 times x to the 15th power times 1 over x to the 15th power. Those x to the 15th powers cancel, leaving us with just -2. So now when we go in and we plug in infinity, wherever we see an x, we get this 1 plus 8 over infinity cubed plus 1 over infinity to the 15th power. And this is all divided by 1 over infinity to the 15th power minus 2. So recall, if we have a number in our numerator other than infinity, which is not really technically a particular number, but if we have a number in our numerator divided by infinity, that goes to 0. And so we have this 8 all over x, or infinity to the 3rd, that goes to 0. 1 over infinity to the 15th goes to 0. In the denominator, that 1 over 15th, infinity to the 15th goes to 0. And so we're left in here with 1 in our numerator all over -2. So our answer in here is -1/2. The next example in here, we have the limit as theta is going to pi halves. I have a negative exponent in there, so it's telling me I'm looking at the limit as theta is going to pi halves on the left-hand side of secant theta minus tangent theta. So again, let's just go through and let's do direct substitution. And so if I go in and I plug in pi halves wherever I see a theta, I have secant of pi halves minus tangent of pi halves. So if we go in and we do direct substitution, well, I know secant is 1 over cosine, and cosine of pi halves is 0. So I'm getting 1 over 0 here, which is undefined, minus over here, tangent of pi halves. So that's sine of pi halves, which is 0. I'm sorry, is 1 all over cosine of pi halves, which is 0. And so I'm getting 1 over 0. And so this is undefined here. We can't have this. This is an indeterminate form, but it's not that indeterminate form where I can use L'Hopital's rule. So I need to go back and I need to manipulate this. So let's go back and let's rewrite secant theta and tangent theta in terms of sine and cosine, and let's rewrite this as a single fraction. And if we did that, we would have the limit as theta is approaching pi halves on the left-hand side. Recall again, secant theta is 1 over cosine theta minus tangent theta, which is sine theta over cosine theta. We have a common denominator, so we can rewrite this as a single fraction. So this is a limit as theta is approaching pi halves on the left of 1 minus sine theta all over cosine theta. So doing this, it hasn't helped. I still have an indeterminate form. I have 0 here over 0, but I have that indeterminate form where I can go back and I can use L'Hopital's rule. So let's go back and let's use L'Hopital's rule here. And so I'm going to just put LH here saying that that's what I'm going to do. And so if that's what you're doing on your exam, if you're in my class, then I want you to state that that's what you're using L'Hopital's rule here and just not jump in and start using it. And so L'Hopital's rule says that if we have an indeterminate form of 0 over 0 or infinity over infinity, the limit that we started with would be the same result as a limit of the derivative of our numerator. So the derivative of 1 minus sine theta all over the derivative of our denominator, in our case, would be derivative of cosine theta. So taking the derivative of my numerator 1 is 0. My derivative of minus sine theta, well, I have that negative. Thinking now of the derivative of sine theta, I know is positive cosine theta, so my numerator is negative cosine theta. And the derivative of cosine theta is negative sine theta. I notice my negatives cancel, so I can look at the limit now as theta is approaching pi halves on the left-hand side of cosine theta divided by sine theta. So if I did my direct substitution in here, I have, this is equal to cosine of pi halves divided by sine of pi halves. So cosine of pi halves is 0 all over sine of pi halves, which is 1. Okay, so this form is okay to get. This is not an indeterminate form. 0 divided by 1 is 0. And so that limit as theta is approaching pi halves on the left of secant theta minus tangent theta gives us back 0. So the last limit problem states the limit as x is approaching 36 of x minus 6 times x raised to the negative 1/2 power. I probably would go through and I would probably rewrite this a little bit. I notice I have a negative exponent, so I could rewrite that by bringing it down to the denominator and making that exponent positive. And so I have the limit here as x is approaching 36 of x minus 6 divided by x to the 1/2 power, which if you want to rewrite that x to the 1/2 power, it's the same thing as the square root of x. So as a limit as x is approaching 36 of x minus 6 all over the square root of x. So let's go in and let's do our direct substitution. Wherever we see an x, we're replacing it with 36. And so doing that, I get 36 minus 6 all over the square root of 36. Well, 36 minus 6, that gives me 30. All over the square root of 36, which is 6. And so we have 30 divided by 6, which gives us back 5. So now we're looking at the second problem. In the second problem, we're looking at the graph that we're given, and we're going to use this graph of g of x to answer the following questions. And so these values in here where we don't have a solid point on our endpoint, we're just going to assume that these are continuing on in the direction that they're going. Okay, so the first question says, let's look at the limit as x is approaching 6 on the right-hand side of g of x. So we're going to locate where x equals 6 is on our graph, which is right here. And we're looking at as x is approaching 6 on the right-hand side. So looking at the right-hand side, we're going to follow the graph in and see what are we getting closer and closer to as x gets closer and closer to 6. And may not even approach, or not approach, but may not even get to 6. And so if we look at this, it looks like that we're getting back approximately x equals 4 as we approach 6 on the right. Part B says find g of 6. So looking at g of 6, notice that on our piece of our graph, as we come in on the left, we have an open circle. As I come in on the right, I have an open circle, but I have this closed circle right here. When x equals 6, my y value I get back is 3. So looking at the limit as x is approaching 6, so in order for a limit to exist, the left-hand side has to equal the right-hand side. I know my right-hand side, we got 4. My left-hand side though, as I'm approaching 6 on the left-hand side, I'm getting back 1. And since those values aren't the same, my limit as x is approaching 6 does not exist. DNE. Part D, we're looking at the value as x is approaching 3 on the left-hand side. So you want to locate where 3 is on the left, or where 3 is for your x-axis, which is right here. And if I'm using this as I'm coming in on the left-hand side of the graph, I'm going to use that piece to the left. As I'm coming in on the left, I want to see what y value am I getting closer and closer to, or approaching and getting to. And so as I'm looking at x is approaching 3 on the left, I'm getting back the value of 5. If I look at the limit as x is approaching 3 on the right, which part E is asking for, I'm getting closer and closer to 3 on the right. I'm getting closer and closer to y equals 0, not really approaching 0, but getting so close that I can say that the limit as x is approaching 3 on the right of g of x is equal to 0. So answering the following questions, I'm going to explain your answer. Is g of 8 a positive or a negative number? So I would locate what g of 8 is, g of 8. So if I look at where x equals 8 and I go up here, my y value that I get back, it's above the x-axis, so it's positive. So g of 8 is equal to, it looks like 5. So it is positive. If I looked at the derivative though, at g of 8, we'll want to know, is that positive or negative? The derivative talks about the slope, or the slope of the tangent line of that function right there. And so if I'm looking at g equals 8, notice that that function is decreasing at g equals, or x equals 8 for that derivative. So I notice that this is a negative number because the function is decreasing which means my slope is negative at x equals 8. Now I want to know, is the double derivative of g at 8 a positive or negative? So the double derivative talks about concavity. I want to see, does that look like concave up or concave down at x equals 8? And so if I'm looking at x equals 8, I notice that this looks like it's a concave down at this piece at x equals 8. If it's concave down, that means my second derivative should be a negative number. And this is because the function is concave down. At x equals 8. Okay, so next part wants to know, is g of x continuous at x equals 5? So 3 things need to hold in order for a function to be continuous at a value. The limit has to exist. So that means that the left-hand side and the right-hand side have to be the same in order for it to exist. The value at that function, evaluated at that function has to exist. And that limit has to equal that value at the evaluated at that function. So at x equals 5, I would need to show if it's continuous that the limit as x approaches 5 exists, and the limit as x approaches 5, if it exists, equals g of 5. Well, looking at x equals 5, I can tell right away that my limit is not going to exist because, or is not going to exist, which means it's not continuous there. So this is not continuous. One of our conditions does not hold true. multiple conditions don't hold true. And I wanted us to explain our answer, and this is because the limit as x approaches 5 of g of x does not exist. Also, we could state that g of 5, notice that there's no solid circle when x is 5. Those are open circles. So also g of 5 does not exist. That's another reason. Or because that doesn't exist, g of 5 doesn't equal the limit as x approaches 5. Next, we want to look at where is the derivative g of x equal to 0. So that's where the slope of our tangent line is equal to 0. So that's where our slope of our tangent line gives us a horizontal value. That would be values where our graph is changing direction. And so notice that at x equals 1, we have a horizontal tangent line. And I also noticed that at x equals 7, I also have a horizontal tangent line. It doesn't look like there's any other spot on my graph where I have a horizontal tangent line. So part K says g of x is not differentiable at what values of x. So it's not differentiable if we have any sharp corners or where our function is not continuous. So there's multiple spots where our function is not continuous. I don't see any sharp corners of our graph, so we don't have to worry about that. But we're discontinuous at x equals 3. We're discontinuous when x is equal to 5. We're also discontinuous when x is equal to 6. Because g of x is discontinuous there. So in order for a function to be differentiable, it has to be continuous and it has to be a smooth curve. Okay, so discontinuous at those values because g of x, or it's not discontinuous, it's not differentiable at those values because g of x is discontinuous at these values. Okay, so the last piece wants us to look at the limit as h approaches 0 of g of 5.5 plus h minus g of 5 all over h. So looking at this problem, I believe that there was a typo when I created this, and I probably had let my students know when they were going through this exam, but I believe that this should have been g of 5.5 plus h minus g of 5.5 all over this h value. If you look at this, this should look familiar, and this should look like the derivative function, the formal definition of a derivative. And so this is asking, what is the derivative of our function of g of x at 5.5? If you locate 5.5 on our graph and go up here, this is a line. And so our line, our slope is constant here between x equals, it looks like 5 and 6. And so we want to find the slope of that line at 5.5. And so we can find the slope of that line at 5.5 by locating 2 points on that line. Let's just look at these open circle. Even though they're not on the line, it's getting closer and closer to this. So I have a point at 5 and 3. And at this open circle here, so when x is 6, I have a y value of 1. So I'm looking at my change in my y value, 3 minus 1, all over the change in my x value, 5 minus 6. So my slope here is 3 minus 1, which is 2, divided by 5 minus 6, which is -1. So my slope at x equals 5.5 is -2 on that graph. And so the limit as h is approaching 0 of g of 5.5 plus h minus g of 5.5 all over h, this is equal to -2. Our next problem here is find the equation of the tangent line to the curve at the given point. Write your answer in slope-intercept form. So we're trying to find the equation of the tangent line of x squared plus xy plus y squared equals 7 at the point 2, 1. And so we need to figure out what the slope is at 2, 1. And so we need to take the derivative of both sides of this equation. Looking at this equation, it's an implicit form, where that means we have x and y on both sides of our equation. And so we want to use implicit differentiation. I noticed that that second term in that equation, x times y, that's a product, and I'm going to need to use the product rule when I go through and differentiate both sides. Whenever I take the derivative of y is a function of x, and so I have to think of it as the chain rule, and I need to tack on that dy dx once I take the derivative of that piece. And so taking the derivative of x squared, I get back 2x plus, so our first function, let's think of it as x. The derivative of x is 1 times the second piece y plus the first piece of that term, x, times the derivative of y, which is 1 times dy dx. Plus, taking the derivative of y squared, I get 2y times dy dx equals the derivative of 7, which gives me back 0. So let's solve for dy dx. Let's get dy dx by itself, get everything else to the other side of the equation that doesn't have dy dx attached to it. And then let's go in and do our substitution so that we could figure out what our slope is. So as I move things over to the other side of the equation, on the left-hand side, let's keep the terms with dy dx. And in the meantime, let's factor out dy dx from both of those terms. And if we do that, we're left with x plus 2y is equal to, let's move these other terms over that don't have dy dx. So subtracting 2x on both sides, we get -2x on the right-hand side, and subtracting y on both sides, we get a -y on the right-hand side. So we can get dy dx by itself by dividing both sides of our equation by x plus 2y. If we did that, we're left with -2x minus y all over x plus 2y. So dy dx, let's go back and use our substitution. For the point 2, 1, I know when x is 2, my y value in here is 1. So wherever we see an x, let's replace it with 2. And wherever we see a y, let's replace it with 1. So going back and substituting in, we have -2 times x, which is 2, minus y, which is 1, all over x, which is 2, plus 2 times y, and y is 1. So we find our slope of the tangent line at that point is equal to, let's simplify, -2 times 2 is -4, and -4 minus that 1 is -5 in my numerator, all over 2 times 1 is 2, plus the 2 gives me 4. So we find that our slope of our tangent line is -5/4. We have 2 points, or not 2 points, we have 1 point on that tangent line, the point 2, 1. And so now we can find the equation of that tangent line. I tend to like to use the formula y equals mx plus b, plugging in what I know y is, which is 1, is equal to my slope, which I know is 5/4. Times x, in this case, is 2 plus b. So we want to solve for b. I noticed before I try to get b by itself that 2 times -5/4, they both have a 2 in common. And so I get 1 is equal to -5/2 plus b. I'm going to need a common denominator, which I see is 2. So let's add 5/2 to both sides of our equation, plus 1 with the common denominator, which is 2 over 2. So 2 over 2 plus 5/2 gives me b is equal to 7/2. So knowing what b is, knowing what my slope is, I know my equation of my tangent line is y is equal to -5/4 x plus 7/2. Okay, so moving right along, let's look at the next question on this exam. So our next question states, for each problem, use the given table containing the values of differentiable functions f of x and g of x and their derivatives. Use the table and the data and the rules of differentiation to solve each problem. So in here, we're given that h of 1, we want to find the derivative of h of 1 of 0, where h of 1 of x is f of x times g of x. So let's first go through and let's find the derivative of h of 1 of x, and then let's go through and plug in 0 wherever we see an x in the derivative. And so notice that we have f of x times g of x. And so when we take the derivative of that, we need to use the product rule. And so the product rule says this is the same thing as the derivative of the first times the second. So f prime of x times g of x plus the first f of x times the derivative of the second g prime of x. So let's go back in here, and wherever we see an x, let's plug in 0. So h prime of 0 is equal to f prime of 0 times g of 0 plus f of 0 times g prime of 0. So now we're going to go in and use our table to figure out what those values are. So looking at when x is 0, we want to look at what is the derivative of f when x is 0. We get that that is 9. All times g of 0, which is also 9, plus f of 0. So plugging in 0 into our original function f of x, we get back 5 times g prime of 0, and g prime of 0 is -3. Using order of operations, multiplication becomes before any addition or subtraction. And so we're going to look at 9 times 9 first, which is 81, plus multiply 5 times -3, which is -15. So we have 81 minus 15. So looking at that, I believe I get back 66. That's correct. Now we want to find h sub 2 prime of 0, or the derivative of h of 2 of 0, given that h of 2 of x is sine x plus 3 times g of x. So I notice here that we need to use the product rule. So let's first look at the derivative of h of 2 of x. Here we're going to use the product rule. So the derivative of 2 sine x plus 3, that first piece. Well, we have 2 times the derivative of sine x, which is cosine x, plus the derivative of 3, which is 0. So the derivative of the first times the second, g of x, plus the first, 2 sine of x plus 3 times the derivative of g of x, which is g prime of x. So now let's evaluate the derivative of h of 2 when x is 0. So let's go back into our derivative function that we found above and plug in 0 wherever we see an x. and then use the formula or the table to figure out what some of these values are. So we have 2 times cosine of 0. Cosine of 0 is 1 times g of 0. So looking at when x is 0, g of 0 gives me 9. Plus 2 times sine of 0. Well, sine of 0 is 0. So 2 times 0 plus 3. All times the derivative of g at 0. So looking at when x is 0, g prime is -3. So order of operations, we're going to multiply 2 times 1 times 9, which gives me 18, plus 2 times 0, which is 0 plus 3. So we have 3 times -3, which gives me -9. So 18 minus 9 gives us back 9. Part C, we want to look at finding the derivative of h sub 3 when x is 1, and we're given that h sub 3 is f of x divided by g of x. So notice in order to take the derivative of h sub 3 of x, we're going to need to use the quotient rule. Wow, that was just a mouthful, wasn't it? So let's go through and first look at the derivative of h sub 3 of x. And so we're going to use the quotient rule, which says I'm going to look at the derivative of my numerator, f prime of x, times the denominator, g of x, minus my numerator, f of x, times the derivative of my denominator, g prime of x, all over the denominator, g of x, quantity squared. So now let's go through and let's plug in 1 wherever we see an x in the derivative function of h of 3. So we have f prime of 1 times g of 1 minus f of 1 times g prime of 1 all over g of 1 quantity squared. So looking at our table to find our following values, when x is 1, okay, so we're looking at our table, when x is 1, what is the derivative at 1? So that's going to give me -3. G of 1, so the original function of g of x at 1 is 2, minus f of 1, so when x is 1, f of 1 is 3, times g prime of 1, so g prime of 1 is 6, all divided by g of 1. G of 1 is 2, quantity squared. So we have -3 times 2 is -6, minus 3 times 6 is 18, all over 2 squared, which is 4. -6 minus 18 is -24. -24 divided by 4 gives us back -6. Okay, so let me pull this piece here and bring it down so I have some room. Looking at the following, we are trying to now find the derivative of h sub 4 of 1, and we're given that h of 4 is a composition of the function f of x of g of x. And so we need to use the chain rule when we take the derivative of h sub 4 of x. So the chain rule says the derivative of the outer, f prime of x, of the inner function, so f prime of g of x, times the derivative of the inner function, g prime of x. So now let's go into our derivative of h sub 4, and let's plug in 1 wherever we see an x. And so we have, this is equal to f prime of g of 1 times g prime of 1. So we're going to look at our inner piece first, g of 1. So when x is 1, g of 1 is 2. So let's rewrite this a little bit. This is going to give me f prime of g of 1, which we just said was 2, times g prime of 1. So g prime of 1, when x is 1, g prime of 1 is 6. So now we need to figure out what the derivative of f is when x is 2. When x is 2, the derivative of f of 2 is 3, all times 6. So 3 times 6 gives us back our answer of 18. Last one for this table is we're trying to find what h prime of, or h of sub 5 prime of 2 is. So looking at h of sub 5 of x, that is equal to f of x quantity squared, which again, if I go through and I take the derivative of this h sub 5 prime of x, I'm going to need to use the chain rule. So my outer function is this quantity squared. So I would have 2 of my inner function f of x, subtract 1 from that exponent just gives me 1, times the derivative of the inside f prime of x. So when I go into the derivative of h sub 5 and I plug in 2 wherever I see an x, this is going to give me 2 times f of 2 times f prime of 2. So using our table to figure out what those values are, we have f of 2. So when x is 2, f of 2 is -5 times, now we want to find what f prime of 2 is. When f prime of 2 gives us back 3. So multiplying this through, we have 2 times -5 is -10. -10 times 3 is -30. So this completes the solutions to the first part of the final that I had given that semester. I'm going to create a second video going over the solutions to the second part of that final. So if you are not in my class and you want to look for that, you can go under Erica Knopfsinger's math lectures and look for solutions to Calculus 1 final part 2.